Looking at this car on the hill example, I start off by not even telling you what the question is going to be. I just start off with some questions for you on how to start interpreting this question. A car in neutral rolls down a 20-degree inclined hill. What is the acceleration of the car in the y direction? Now, notice something vitally important. I have changed the y direction, and the x direction for that matter. I've put them on an incline. I put this whole thing on an incline. The x direction is pointing down the hill. The y direction is pointing perpendicular to the hill. This is the first of many things that many of you are going to be annoyed with in this problem, that I have unilaterally changed the axes here. Well, changing the axes in this way is actually really helpful for making this problem easier to deal with. If here's a hint, I'm going to eventually ask, what is the acceleration of the car down the hill? Well, if you have to have the x and y directions being the traditional x and y directions, where y is straight up and x is completely out to the right side, then you're going to have an acceleration in mostly x, but a little bit in negative y, and so the acceleration you get will look funky. So if we rotate our axes somewhat so that the car is going to be going only in positive x, that actually simplifies what we have to do quite a bit. This also means that we're going to have forces we're going to have to deal with fewer components of forces, which I'll get to in a bit. Question for us to consider right now is, what is the acceleration of the car in the y direction? That's kind of silly. It shouldn't be accelerating in the y direction, right? Not in this y direction. Y direction being perpendicular to the hill. If it accelerated at all in the y direction, then it would either fly off the hill or dive into the hill. Accelerating in the y direction would mean that it would have to eventually change its y position. Right now, as it just rolls down the hill, the y position should stay 0 the entire time. But now, but because of this change in axes, well, it had better just stay in 0. It should stay 0 for y the entire time, because if it doesn't, then that would imply that it's either leaping off the hill or diving through the hill. So all the acceleration, all the motion should be just in the x direction. Question for your consideration again. A car in neutral rolls down this hill. In which quadrant would the force of gravity point? If we apply our normal quadrants, so quadrant 1 is positive, positive, quadrant 2 is over here, quadrant 3 is negative, negative, and quadrant 4 is down here at the bottom in this case, then in which quadrant is the force of gravity going to be pointing? Yeah, the fourth quadrant. Excellent. Force of gravity is still pointed directly towards the center of the Earth, and the direction to the center of the Earth is not going to change whether or not you're on a hill. It's going to be straight down towards the center of the Earth. And straight down does not necessarily mean in the negative y direction. This is an example where straight down is not the negative y direction, which is an interesting departure from what we've done. What force actually causes the car to roll down the hill? This is more easily explained with some diagrams. Here, I've drawn you a free body diagram of the car on the hill. There are two forces acting on this car. We're going to assume that there's no friction here, because we haven't talked about friction yet. We don't know how to deal with friction mathematically. We've got the force of gravity pointing down towards the center of the Earth. We've got the normal force pointing normal to the surface, remembering that normal means perpendicular to. So normal does not point directly up, it points perpendicular to whatever surface. And now that we finally have a tilted surface, we're going to have a normal force that is perpendicular to that tilted surface and not just straight up. If we take our axes to be like this, with positive y going perpendicular and positive x going down the ramp, then we can take each force and break them into their components. Looking at this, the normal force should be all in positive y, like that. It's not straight up, but it is just in positive y because we've tilted our axes. On the other hand, the force of gravity is not going to be just in negative y. It's going to be partially in negative y. So positive y, positive x, negative x. It's going to be partially in negative y and partially in positive x. I've drawn that down here. I've drawn the force of gravity pointing down. I've drawn well, you can see the axes like that. So imagine superimposing that down there. That is the positive y direction, and that is the positive x direction. And so the components of a vector must fall along the axes that we're dealing with. And so the x component will be that shadow of the vector. So here's our force of gravity vector, here's our shadow of that vector. And we do the same thing for force of gravity in the y. Here's our force, here's our shadow of that force projected along the y-axis, like that, similar to projecting our shadow along the x-axis, like that. Will we neglect friction in all cases? No. By probably Thursday, if not Thursday, then Monday, we will actually be dealing with friction. But for now, because we haven't really covered friction yet, we'll be doing a bunch of frictionless problems, and then I will complicate everything by taking all the problems that we've done before and throwing friction into each of them and making each one of them more complex than they were before. So that's fun for some people like me because I like physics. Well, we know that we're going to have to eventually find the x and y maybe components of the force of gravity. How do we find the components of a vector when everything is tilted like this? We don't have the nice situation anymore that we did before because we've tilted everything. We've got components going off in angles that we're not used to. How do we actually turn this into components? Well, this is where you have to remember a whole lot of trig from forever ago. I tell you here that the angle of the slope, the hill, is 20 degrees. So I can recreate that down here. That's 20 degrees. Okay, well, if this 20 degrees, I'm gonna just casually continue that line all the way over here, like that. Okay, maybe I can continue it on over there. Maybe, yeah, I guess that right there has got to be a right angle. Oh, that's a good hint. Oh, also, the angle between any two components has to be a right angle. The y direction has to be at a right angle to the x direction. We can create this triangle here. Now, this is annoying to actually draw, but we've got this gigantic triangle right there that kind of encompasses a whole bunch. This angle right there is 20 degrees. That means because this triangle that I've just drawn here, going from the tip of this up to here, down to the bottom of the ramp, back to the tip of that angle has to be 70. This in here has to be 70 degrees. Okay, because that's 20 degrees and that's 90. So if that's 90 and that's 20, that has to be 70. Then I can focus down more closely. Let's just look at this little triangle now. I've got this little triangle right there. That is 70 degrees. Therefore, this has to be 20 degrees. Okay? And if that right there is 20 degrees, and if this is parallel to this, then that's also 20 degrees. Oh dear, there's so many lines and so many scribbles on this now. It looks awful. But the point is, I'm looking for FGX, which is that right there. This is a triangle. That's 20 degrees. This is opposite that 20 degrees. This FGX is opposite that 20 degrees right there. And because that FGX is opposite that 20 degrees, you can say, oh yeah, SOHCAHTOA. SOHCAHTOA tells me that if it's opposite, S-O-H, SOHCAHTOA, S-O-H, opposite over hypotenuse is the sine. That's the opposite. Therefore, the x component is suddenly going to be the sine of 20 degrees. The x component is the sine of 20 degrees. In all the previous problems, the x component was the cosine of the angle. We can do it again, and we can say, okay, we're looking for this right there. That's the y component of the gravity right there on that side. That's our 20 degrees, and we're adjacent to our FGY is adjacent to the 20 degrees. Adjacent, SOHCAHTOA, C-A-H, cosine is adjacent over hypotenuse. The y component, the way that we've drawn it, is going to be the cosine instead of the sine, which it usually is. This is the other really annoying thing about this problem. Everyone hates tilting your axes, and everyone hates all this. Oh dear, because it gives us exactly the opposite of what we're used to. Yeah, it's backwards from everything that we're used to. And it's difficult to look at a problem and decide just by looking at it what you're going to need to do. Therefore, I gave you some problems on the homework where you actually have to look at this kind of thing. There's also a great example. I don't remember offhand what example number it is. There's a great example in the book that does exactly this. I will post an additional video that I did not create that explains this a lot better than I can. It's a Khan Academy video, and it explains it super well, why you have the angles doing the things that they're doing. Stefan says just flip the paper around and do the problem upside down. That's actually a perfect way of doing it. If you flip everything around and look at it like this, then it actually all kind of makes sense. You can take that 20 degrees, or you can adjust things like that. You can look at it at different perspectives, and that might help you understand what's going on. I'm going to post that video, and I hope that the video helps everyone understand it in some way. Whichever way you understand it, as long as you understand it, that's fine. And if you have any questions, what I'm going to do is tell you watch that video, and then if you have questions, then tell me. So I will post that video shortly after class, and I'll send out an announcement. What else can we do with this? Now that we have our FGX and FGY components of gravity, then we can do exactly what we've always done before. We can have F net Y or F net X, it doesn't really matter. F net Y is equal to MAY. We already determined that acceleration in Y is 0 because the car is not flying off the ramp and it's not diving into the ramp, it's just going along the ramp. And so the acceleration in Y should be 0, otherwise it would fly off the ramp or burrow into it. Therefore, the normal, which is going in positive Y, opposes the Y component of gravity, which is going in negative Y, like that. And that should equal 0. So we find that the normal should equal the force of gravity in the Y direction. The normal is equal to FG cosine theta. Plug in the numbers, and you get whatever you need to get. I'm not actually asking for the normal force here. I just thought I'd show you how you would find that. I am going to ask for the for the x acceleration, for the acceleration in the x direction. Excuse me. We find the acceleration in x the same way we found anything else. We say F net x is equal to max. The net force in the x direction is equal to the mass times the acceleration in the x direction. We look at our problem, and we write down everything that's going in the x direction. Well, what all is going in the x direction? We only have two forces, and there's no x component of normal. There is an x component of gravity, and so the only thing that's going in the x direction is gravity. This means that gravity is the force that pulls your car downhill. It's the x component of gravity that pulls your car downhill, but it's still just gravity pulling your car downhill, which actually totally makes sense, that gravity is going to be the thing that pulls your car downhill. It's just a component of gravity. So we have FGX, which is equal to FG sine theta. We can plug that in right there. The force of gravity is equal to the mass times the acceleration due to gravity. So I can say force of gravity is mg. But now I have mg sine theta is equal to max. I've got a mass on both sides. I can divide both sides by m, get rid of mass. You can see that means that the acceleration should not depend on the mass of the car, which is also what you'd expect. The acceleration, if you drop a heavy ball and a light ball off of the Leaning Tower of Pisa, famously, they should hit the ground at the same time because they accelerate at the same rate, 9.8 meters per second squared. This isn't going to be quite 9.8 meters per second squared because it's on an incline like that. And so you solve a little bit more. AX is equal to G sine theta. And plugging in 20 degrees, we find the acceleration in the x direction is 3.35 meters per second squared. We can do the same thing that we did before, looking at other angles, other amounts of things. Let's look at other angles. What if the angle of the hill was 0 degrees? What if there's actually no angle to the hill and it's actually just flat ground? You'd plug in 0 degrees, so sine of 0, let's see, the sine of 0 is 0. And so the acceleration would be 0. Oh, well, that means if the hill wasn't a hill and it was actually completely flat, then your car would not accelerate just by putting it in neutral. It wouldn't roll down the hill. It would just sit there, which is exactly what you'd expect by putting a car on flat ground and putting it in neutral. It should just stay there. Well, what if we made the angle 90 degrees? What if we put the car on the side of a cliff? A 90-degree cliff, and we just let it roll down that 90-degree cliff. Well, there wouldn't be a whole lot of rolling. It would just fall down. Sine of 90 is 1. G times 1 is 9.8. The acceleration, if you just put a car on the side of a cliff and let it go, it would accelerate down at 9.8 meters per second squared, which, again, is exactly what you would expect from putting a car on the side of a cliff. Don't do any of those things. You know what? Note, disclaimer for everything, never actually try any of the example problems that I give you. It will probably end in doom and destruction. So avoid my example problems throughout the semester. Here is the last example that we're going to have time for today. It has a lot of similarities with the last one as well. A sled is tied to a tree on a 30-degree incline. The sled weighs 77 newtons. Okay, that means that the force of gravity on it is 77 newtons. What is the net force on the sled? So this is, again, I'm not asking you the final question. I'm asking you things to think about as we go through. A sled is tied to a tree on a 30-degree incline. Do you think the sled is moving? Do you think it's accelerating? I don't think so. I think that if we've tied the sled to a tree, like, you know, just and put it on the hill somewhere, then it probably should not be accelerating. And so the net force on that sled should be 0, right? If it's not accelerating, the net force should be 0. Okay, so the net force in X should be 0, and the net force in Y should be 0. Now, the actual question that I want to ask, how much tension is in the rope that you've used to tie the sled to the tree? And what is the normal force on the sled? Because it's still lying on the ground. Here we have the setup. We've got a tree, we've got a sled attached to that tree. I think most physics textbooks are written by people from places with hills and snow and stuff, because I got these examples right out of this textbook and a previous textbook. And this one only makes sense if you have sleds and snow and hills, and the previous one only makes sense with hills, which we in Florida don't really have either of. But you know, if you've ever seen a sled, you know, you might tie it to a tree before you're going to go sled down the hill or something like that. We need to find the tension and the normal force on this sled. And I give you my version of the free body diagram. Let's talk about it. We've got a sled. It's presumably on planet Earth. If it's on planet Earth, you're going to have the force of gravity on it. Check. Okay, it's tied to a thing. It's tied to a tree. So, therefore, you have to have tension in the string, in the rope, whatever. And it is resting on the hill. And so because it's physically touching the hill, you're going to have a normal force acting on it. Okay, well, what do? We break it up into X and Y, just the same way we did with the previous problem. Very often when you've got hills, when you've got inclines and angles, you're going to do this right here with your X and Y axes like that. So get used to doing this kind of thing. If we look in the X direction, we have the normal equation. The net force in X is equal to max, but we know that the acceleration in X is 0 because it is not sliding down the hill. And we know that the net force in X is going to be all the positive X forces minus all the negative X forces. Well, positive X. Normal doesn't go in positive X. Tension goes in negative X, the way that I've drawn it. Oh, but force of gravity is going to have a positive X component and a negative Y component, like that. So this here is going to be FGX, and this here is going to be FGY. Those two components, like that. Our positive X component is going to be FGX, the force of gravity in the X direction. The negative X component is going to be the tension from the string, or the rope. So we can write that down. FGX minus tension. X component of gravity minus the tension force. That's everything that's going on in the X direction. But what was AX? Oh yeah, that was 0. So I can replace that side with 0. And I can replace FGX with FG sine theta for the exact same reason that we had that before on the previous problem with the car. Same trigonometry, at least. And then algebra, force of gravity times the sine of theta is equal to the tension. And force of gravity is mg, but as I was doing this problem, I forgot that I had already given you just the weight. And force of gravity is equal to the weight, and the weight was equal to 77 newtons. So I kind of did too many steps. I should have just gone Fg to 77 newtons times the sine of 30, because I told you that the angle is 30. That's equal to the tension. This is just a number. You ask your calculator, you get 38.5 newtons for the tension in the string. This is very important for any budding material scientists out there who want to make sure that their strings don't break when they use structural things like that in their designs. I guess that's also for just any kind of engineer, really. So the tension is 38.5 newtons. We can do the exact same thing in the y direction. F net y is equal to MAY. The y forces are going to be the normal force right there, minus the y component of gravity right there, normal minus y component of gravity is equal to MAY. AY is 0 again for the exact same reason. We don't expect this sled to be moving. Normal minus FG cosine theta, because when you've got things at these kinds of weird axes, then you flip which one is sine and which one is cosine. Y becomes cosine, X becomes sine. Again, I'll post that video, so look at that video. Doing a little bit more algebra, we see that the normal force is equal to Fg cosine theta. Fg is 77 newtons, theta is 30. The normal is equal to, well, let's calculate that, 66.7 newtons. We have found the tension and the normal for this sled on the hill, just as we set out to. The next question is about a fish in an elevator, which is another classic kind of physics question. We have weird ways of expressing things sometimes. The question, you can read this in the slides, is we've got an elevator and we've got a fish on a scale. And when the fish is just sitting on the scale and the elevator is not moving, the scale reads 4.08 kilograms. And when the elevator starts accelerating upwards, the scale will actually read a different value. Now, you all know that this is probably true. If you are standing in an elevator and it's just sitting there, then you don't really feel anything weird. But if the elevator starts accelerating up at the very beginning of its motion upwards, you'll feel heavier very briefly. You'll feel heavier as it accelerates upwards, and then it'll get to a constant speed and you won't feel anything anymore. And then when it gets to the top of its motion, it has to slow down and you'll feel lighter at the very top of its motion. When you get to the top floor, you very briefly feel lighter as you're getting to the top floor. Same thing if you're going down. When you start going down, you feel a little bit lighter. And when you get to the bottom and it stops, then you suddenly feel a little bit heavier at the bottom. We can actually calculate what a scale would read and see what you'd get in any of these kinds of accelerations. I do not recommend that you take a scale and a fish into the physics department elevator and just leave it in there and walk away. So don't do that. Disclaimer, disclaimer, disclaimer. But people would get the joke, but just don't do it. So everything is happening in the y direction. Everything is in the y direction here. So we can just say F net y is equal to MAY. There are two forces acting on the fish. The fish is sitting on a scale, and so the scale has to be giving it a normal force because the scale has a physical surface and the fish is resting on that scale, so it has to be pushing up. So we've got the normal from the scale underneath the fish minus the force of gravity on the fish is equal to, well, F net y is always equal to MAY, so MAY right there. Mass of the fish times the acceleration in y of the fish. Well, if the elevator is just sitting there, or if it's just moving at a constant speed, then AY is 0. But if the fish is in an elevator which is accelerating up or down or whatever, it doesn't even matter, AY is not going to be 0. You're going to have some value for AY. In the question, I pose to you that the elevator is accelerating upwards at 2 meters per second squared up. That's the acceleration. So we have the normal force on the fish minus the force of gravity is equal to MAY. The force of gravity is mg. And we are solving for the normal here. In this, we're solving for the normal. It turns out that normal force is the way that you feel weight. This is not 100% accurate, but it's how we're going to view this kind of thing. Let's say that you put on a really, really heavy backpack and you just stand in the middle of a room, then you feel heavier. If you put on a really heavy backpack and you just stand there, you personally feel heavier lifting up that big backpack. The reason that you feel that is because the floor is having to push up on you with more force. If the floor pushes up on you with more force, that's how you feel weight. If you go to Mars, your mass stays the same, but your weight decreases. You don't have there's no like physical sense where you can feel the gravity on you. There's sight and there's hearing and there's taste and there's touch and whatever. And there's no sense of gravity. There's no organ that feels gravity, but you can definitely feel the ground pushing up on you more or less when you're on a different planet, or when you're in an elevator that's accelerating differently, or when you're on a roller coaster ride and you feel like you're being lifted out of your seat or crushed into your seat. That's not the gravity you're feeling. That is the normal force of the seat that you're sitting in. So your normal force is how you feel your weight. And it's in fact also how a scale would read your weight. We can plug in your acceleration in y, 2 meters per second squared there. So we get the mass, which we already found, 4.08 kilograms, times your physical acceleration in y, 2 meters per second squared. And I already did a little bit of algebra to get to this step. We've got mass times gravity. I added mg to both sides. We see that the normal force on that fish is 48.2 newtons. But 48.2 newtons, 48.2, if you divide that by, or actually, let's take just 9.8 times 4.08. The normal force on the fish should be 39.984. I guess I was taking 40. So it should be about 40 newtons if it's just 9.8 times 4.08. But the normal force is 8.2 newtons larger than what we would expect. That 8.2 newtons larger than what we would expect would get translated into what the scale reads and give you an effective mass. Now, this is not actually something that I'm going to test you on. I just thought that this was neat. And so you don't have to worry about terms like effective mass. So kind of ignore a lot of this. I could ask you a question where I tell you to find the normal force on the fish, for example, but doing this extra step, you don't really have to deal with it. I just thought it was neat. A scale just takes the normal force that it's outputting and divides it by 9.8 meters per second squared, and it gives you your mass like that in kilograms. Scales, of course, give you things like kilograms, not newtons. You don't step on a scale like, oh, I want to see how much I weigh now. You step on a scale. Well, if you got the scale in America, it's going to read pounds, but if you got it anywhere else, it's going to read kilograms, even though technically that scale is measuring your weight, not your mass. It should be giving you your weight in newtons, but nobody likes that. So it gives you a weight, it gives you a mass in kilograms, but it does that by just taking how many newtons that it's applying to you, 48.2, and dividing by 9.8 meters per second squared to give you what it thinks is your mass. And so you'd get 4.91 kilograms doing this. The actual mass of the fish is 4.08, but if the elevator is accelerating up, then that fish seems to have a greater effective mass like that.